With respect to the right-hand rule, now you don't need to know a lot about the right-hand rule, I don't think, in A-level further maths, but I'm just going to talk about it briefly. It's when you have your axes orientated in a specific way. So if you hold your right hand out and point your thumb, your first index fingers, so they're all perpendicular, then you should be able to orientate it so the axes fit along that. So as opposed to the y-axis going in the opposite direction, that would then be you following the left-hand rule. And you have to have it like this if you want to use certain formulae like the one given. Um, Otherwise, you have to adapt the matrix for this anti-clockwise rotation about the z-axis. Because if it was pointing down, for example, then it's like it would be actually that would be making it go clockwise. So in any case, we're using this right-hand rule system. We're given this is the general matrix and then a specific matrix M which is a rotation through alpha degrees anticlockwise, and we're asked to determine the value of alpha. So what I can do is look at cos theta equaling minus root 3 over 2 to find theta. First solution is 150, and then we do 360 minus to give 210. So I'm not sure which one it is at the moment, but now I check the sine theta, which is minus a half. If you do inverse sine of that, you get minus 30, but you can find the other two solutions, which are 210 or 330. So we can see it must be 210. Let's determine the smallest possible positive integer value for k, for which m to the k is equal to I. So remember, this is a rotation, and so we're just going to keep rotating it until we get back to pointing the same direction we did at the beginning, which is going to be some whole number of 360. So every time I rotate, like I'm going to rotate k times, I will have rotated 210 times k, first time 210, second time 420, and so on. And that must equal 360 times n, the sum integer n. That's how you're going to do this question. We can, so for whole number of rotations, I can divide through by 10 and the common factor of 3 to give me 7k equals 12n. So therefore k must equal 12 over 7 times n. That means n must be a multiple of 7, because it's a whole number, remember, and k is going to be then 12 times that. Basically, k is going to have to be a multiple of 12, and the small, well, n could equal 0, obviously, when there's no rotations, but it's a positive integer. It's actually applied to these transformations. So the smallest positive integer value of k is going to be 12 when n is 7. Right, now we're told that the 3 by 3 matrix N represents a reflection in the plane with equation y equals 0. So we have a point here, it's going to go to here. This is y equals 0. So essentially, the y value, if it was say minus 3, it's going to jump to 3. It's going to change sign. The x and y are going to stay the same. Because maybe x is going this way and z, I don't know if this is a right-hand system, but z is going into or out of the page. So write down the matrix that creates this. Well, you might have learned this. I tend to just try and figure it out each time. Because I know afterwards I've got x minus y and z. So then I just think, what matrix would give that? Well, I don't want anything to happen to the x, and then I don't want any y's in the top, so it's going to be 1, 0, 0. Then I want y to become minus y, so I need a minus 1 there, no x's or z's going in there, and then 0, 0, 1. So that's going to be my answer for n. So the point A has coordinates minus 2, 4, 3, and that B is the image of point A and the transformation represented by M, followed by N. So let's just get that straight. It would be N on the left, and then M, and then the coordinate, which I'm going to write as a position vector, which will give me my position vector for B. So we are going to have 1, 0, 0, 0, minus 1, 0, 0, 0, 1. multiplied by that vector from above, this one, which is this. Of course, you could program this into your calculator. And then we're times and by the position vector for A, but I'm going to do it by hand. Now you can decide on the order. The order doesn't matter, but it's probably going to be best to times the first two together first, because it's just a little bit easier, I think, with so many zeros going on. And this ends, I mean, I'm not going to go into detail. Maybe I'll do the first, like, so we've got this row and this column. We're just going to get minus root 3 over 2. And then we get a half, 0, half, root 3 over 2, 0, 0, 0, 1. And then we do this times this, which ends up giving root 3 plus 2. And then the next row down, minus 1 plus 2 root 3, and then 3. Which means that, therefore, B is going to be 2 plus root 3 to root 3 minus 1 and 3. So O is the origin, and we're asked to show to three significant figures the size of angle AOB, that it's 66.9. So this was part E. What I can do is put the origin down, and then, okay, of course, we're working in 3 dimensions here, but I'm just going to represent it with this 2D sketch. We're trying to find the angle here in this triangle. So what I want to do is work out some of the lengths. I know the coordinate for A, so therefore I can find the length OA. And this is going to be minus 2 squared plus 4 squared plus 3 squared, all square rooted. That ends up being root 29. I can do the same for B, which is going to be 2 plus root 3 squared plus 2 root 3 minus 1 squared plus 3 squared, square rooted, which is also root 29. Actually, we could have thought about it. We're applying a rotation and a reflection, and it's going to stay the same distance from the origin. When you have like a point here and you reflect it in the y-axis, it's still the same distance away. If you then like rotate it over here, it's still the same distance away. But I think it's good to be careful, to be honest. And then we can also work out AB. Sorry, I've got like so I can find the distance between 2 points, and then I'll go with minus 2 minus 2 minus root 3. That's the difference in the x values squared, plus 4 minus 2 root 3 plus 1 all squared, plus 3 minus 3 all squared. Actually, that one just cancels out. And this equals, I'm going to leave it as a third, the square root of 56 minus 12 root 3. So now let's use the cosine rule. That is that side there. So therefore, I'm going to square this one. 56 minus 12 root 3 is going to equal 29. That's root 29 squared plus 29 minus 2 times root 29 times root 29 times cos of angle AOB. If you rearrange that, you get cos angle A OB equals 0.3928, which gives angle AOB equal to 66.868, becomes 66.9 degrees. And then for the last bit, hence determine the area of this triangle. So we now have this angle, 66.868. We've got the two sides. We can use a half AB sine C to get the area. So half times root 29 times root 29, so just 29, times sine of 66.868. I'd like to use the non-rounded version. And then this gives 13.3 to three significant figures. Well done.